All right, so we're gonna cover impulse functions. All right, so maybe something you guys have seen before, but basically the next kind of unit of stuff we're gonna cover, which is really the rest of this week and next week, some stuff on function manipulation and kind of introducing another kind of core odd signal that we use oftentimes in these ECE problems, which is the impulse or the Dirac delta. Anybody heard of that before? Either differential equation, which is good. So when Yahoo asks you about it next semester, tell them that you know what it is, because normally you guys say you don't when you get to 3111. So if you covered it in 2 classes, I sure hope you remember it. Hopefully I don't take it out of your memory by the time you're done. But impulses in the Dirac delta, same thing. We're going to talk about what those are, and the properties of those sorts of things. So one thing, I use this term a lot. I talk about signals, right? What is a signal? Anytime I use that term, right? It's some sort of real world information that can be modeled with a mathematical function, right? So if I say an A note in music, right? So if I had a tone that was an A note, what is an A note? Anybody know what frequency that is? 440. Yeah. All right. That means that basically this guy is, if I had to give a model for that, what would it be? If I had to create a mathematical model for an A note, what would it be? What's that? Well, so if I talk about a signal, I'm talking about something that exists in time typically, or always, right? So it's some sort of a time signal. So what would it be for what's a 440 hertz signal? It would be A times what? Cosine 2 pi 440 t plus some shift, right? And the shift doesn't really, your ear can't hear time shifts necessarily. So, and this isn't totally true, because this implies that A note lasts from t equal negative infinity to t equal to infinity. So it actually is a little more complicated than that, because certainly an A note we're not always hearing one, right? So this only lasts for a certain period of time, but you get the basic idea, right? So we use that term signal a lot because what it means is it's representing some kind of information that exists in the physical real world. All right. So there's a whole number of classical signals that we deal with. Sines and cosines are the most common, right? These guys here, we're going to talk about these more. These are all defined in chapter 2 in the book, but these are obviously, as we know, all closely related to this e to the j omega t idea. Right, we're going to talk more about that as we get into our next topic, which is Fourier. All right, and Fourier gets into dealing with this, where I have additive combinations of sine and cosine. So one thing you may have heard of, so in digital circuits, right, you have clock signals, right? What's a clock signal look like? Yeah, so it's a repetitive pulse like this. This is what I would call sometimes a square wave. All right. This guy turns out to be an additive combination of sine and cosine. All right. A very common type of signal to have. Anything that repeats, anything that's periodic is an additive combination of sine and cosine. Then unit steps are pretty common. Actually, I can think of this somehow in combination of unit steps, right? If I say the unit step, that's u of t. And what's my definition of u of t? Yeah, so it's 1 and 0. Where is it 1? What's that? Well, but for what values of time is it 1? Yep. T greater than 0, t less than 0. It's a little ambiguous. I usually write it that way. So it's at t equal to 0 that it makes its change. And then another common one is this Dirac delta, which we're going to deal with. And in fact, if I were to better model this A note, what I probably would do is say, well, if it lasted for 2 seconds, what I probably would do is actually multiply this by u of t minus u of t minus 2. If it lasted for 2 seconds. Now, I don't expect you to fully appreciate that in your head just yet, but we're going to deal with that type of thing here in a little bit. Okay. So the other guy that we deal with is the Dirac delta. So if you know what it is, what is it? It's a line. So what is a Dirac delta? It's a point. Yeah. Well, I didn't say anything. Well, you guys said you kind of knew what it was, so or somebody did. Okay. You know it in relation to Laplace. The question is what what is it? Anybody? No one knows really what it physically probably is, just how it relates to the Laplace. Which is fine, right? Way I think of it in this case is if I have a rapid change in energy, right? If I have something like this, all right, so somebody hits the ball, right? In that particular case, oh, we got Newton's second law again, right? So force equals mass times dv dt, right? So in this case, what's happening? The ball comes in at 90 miles an hour and hits the bat and changes its velocity, right? Its velocity is, coming towards it and then away. So in this case, the force is coming from the bat. How long is the bat hitting this thing? How long is the bat in contact with the ball? Fraction of a second, right? Very short time. This is the kind of thing that we think of with an impulse. Basically, if I think about what the force would look like if the ball were to come into contact with the bat at t equal to 0, the force would be pretty high, and then it would pretty quickly go to 0, right? Very short period of time. So basically what I have is some kind of a short pulse. Right? Some kind of a short pulse, which is a pretty common thing to have. And this is a useful kind of model to have in a lot of situations where I could say, what would happen if that pulse became so short that it was almost exactly 0, right? And that's a reasonable way to model a lot of things. Like in this case, do I care that the ball's in contact with the bat for 1 millisecond? Or is it close enough to approximate it by saying it's just it touches it and it's gone, right? So the way we deal with this typically, and we'll think of a real place where I can apply this, is this idea of if I had something like I just had, and the definition of the Dirac delta function of the impulse, it's an ideal signal, right? And I say if I took this guy here, basically if I said, let's shorten this pulse, let's move this guy here so he's moving closer to 0. So what I'm going to say is I've got this pulse, which has a height of epsilon and a width here of 1 over epsilon, okay? And then I'm going to let epsilon go to 0, okay? But before I even think about that, what's the area under this guy? What's the area under that curve? So epsilon is the height. The width is what? 1 over epsilon. So the area is equal to 1, right? And that area can be thought of, I don't know, if I called this function here, if I called this f of t, right? I could write this as the area under f of t is that, okay? So let's say, I guess in this case, what I'm actually doing is letting epsilon go to infinity, the way it's written here. If I let epsilon go to infinity, what's going to happen to this height? Well, it's going to go really big. What's 1 over epsilon going to do? Go to 0. What we do is we say in the definition that we do that, if we let that width go to 0 and we let the height go to infinity, what I get is this function here, and I represent it this way. Now, what is its meaning to me? Well, its meaning to me is this idealization, as I wrote here, an idealization of a signal that's very large near t equal to 0, very small away from t equal to 0. In other words, it's basically it's real high, and then it's basically nothing. And it has an area of 1. All right, the area under it is 1. So it's basically something that's really large but doesn't last for very long. All right, and that's a way of thinking about something like this scenario right here. But it's also a way of thinking about some other things that are fairly common, which we'll deal with here in a second. All right, but if I think about it like this, here's the definition that I have for it. All right, so I express it like this. All right, so I draw an arrow with a head on it, and I say this function here is delta of t. All right, so delta of t, so that's why it's the Dirac delta. It's a lowercase Greek delta. All right, it's located at t equal to 0. And what I say is the area under this guy is equal to 1. So in this case, notice I've got limits on my integral. Okay. Here is A somewhere on the left side of that guy. Here is B somewhere on the right side of that guy. Okay. If I told you A, so I guess this is the important thing. Really, to be clear, the area under, as long as the bounds that I have include the impulse, the area under that thing is 1. Okay. Nothing all that particularly exciting going on here, right? But it's a pretty useful function for us in a lot of ways. And I'm going to jump around because I want to deal with one way that you guys could probably think about this. All right, let's say I had this circuit, not that you guys want to think too hard about circuits here, probably. But let's say I had a switch that was running. It was closed for a long time. All right, and at t equal to 0, the switch opens. And let's say this was a 12-volt battery, and this was a 1-ohm resistor. So it's DC. That thing's been running for a long time. What was the initial value of the current? So let's call this IL here. IL equals L di dt. Well, EL equals L di dt. Okay. All right. So it's a pretty real world problem. You do this all the time, right? So when you unplug something, this is a situation I run into when I unplug something, right? So what's my initial value of the current? So what would the value be right before? So 0 minus, I suspect Yahoo uses that with you guys. So 0 minus, what's that mean? Right before t equal to 0. Okay, so right before t equal to 0, if this is a DC circuit, what is IL of 0? Switch is opening at t equal to 0. 12 amps. All right. 12 amps, right? So what would Yahoo tell you IL of 0 plus always is? How is that possible? Sure it can, because there's no path here. Right? I just broke what Yahoo always told you. Now, Yahoo tells you that because there's always a path in the circuit he gives you. All right. But in this circuit, there's not a path. And you've seen this before, right? If you have a load that's running and you saw all of a sudden yanked it out of the wall at t equal to 0, what happens when you yank it out of the wall? You get some sparking. All right. Now, why is that? Because what's the voltage going to do across that inductor? It's going to become infinite. Right? So how do I know that? So if I think about what the current looks like here, the current would go, if I looked at t equal to 0, the current would be going 12 amps and then somehow going to 0 amps like that. And I know that VL is the derivative of it. Right? So and this is something, if I really make that happen in 0 time, in other words, this thing turns off, like it immediately from t equals 0 minus to 0 plus, this guy goes down. What did they tell you in calculus is the definition of the derivative at that point? It's not defined. Well, we're going to define it with the Dirac delta here. So we can kind of make some sense of this for a second, right? So if I look at this, let's say I have a ramp function like this. So I have a function that's 0, and then it goes up for a while to 1, and then it levels off at 1. What would the derivative of that function look like versus time? So from here to t equal to 0, what would the derivative of that function look like? 0, right? So it'd be 0. And then what happens at t equal to 0? You got a line, and that line has a constant slope. So what would the derivative be? Yeah, so what's the slope here? So it says that my slope is the rise over the run. So I rose of 1, right? And I said I've got a time t here. So rise over 1 would be 1 over t. So that would be like this, right? So I'd go up. And then when I got to time t, what would happen? Go back down. Yeah. And I'd level off at 0. So this height would be 1 over t. So this is my derivative d by dt on the bottom. Now what happens if I if I basically make that time shorter and shorter? The slope's going to get higher and higher, isn't it? Right? Until eventually it's so high that it's happening in 0 time. That derivative basically would be, if I said, okay, what's my rise here? My rise is 1. What's the run? It's 0. So that I've got this 1 over 0 situation. This is where I draw my impulse. So basically what we're saying is the derivative is 0 until it's almost infinite and then goes away. So what's the value of this function at that point? We say the value of that function is undefined. All right, so in other words, we draw this guy, and we're going to see this a lot. We usually write a number 1 next to it. That is its area. It's an impulse of area 1. Okay. All right. It's not to say that it has a height that's 1. It has an area that's 1. Technically, its area is undefined. And this is what really happens. So basically, when I see that sparking going on, basically because there is an absolutely enormous voltage that is appearing across that thing, until at some point the laws of nature cut in and say once the voltage gets big enough, there's going to be an arc that occurs. Okay, that's basically what you see when you unplug that stuff. In a circuit, Yahoo gives you, yes, IL of 0 minus IL of 0 plus is always going to be equal to each other. He's not going to give you this circuit here. All right, it's not a common thing to really think about, but it does commonly happen. All right, so that's where this guy would apply a lot, is when I get into a situation like this, and I have to think about this type of a situation where I have a quick change in something. All right, so I'm gonna go back then to some of these kind of formal properties of this guy. I basically say delta of 0 is not really defined, right? I know that delta of t is equal to 0 for t not equal to 0, okay? The other thing I'm saying is here, all right, if this is time and this is delta of t here, all right, if A is here and B is here, my area is 1. And this other definition I have, very formal definition, doesn't mean a whole lot to me per se, but if I say I have delta of t like this, and I had A over here and B over here, what's that area going to be? If I take this integral over that function in that window, what's it going to be? 0, right? That's this situation. All right. So, and basically when it's saying when my bounds don't include the delta, all right, that's the scenario I get to. It's not a particularly fancy thing I need to think about too much. All right, now the thing that I also point out is that this guy is ambiguous if either of the boundaries I have are 0. Okay, in other words, when I say here, if I do this from 0 plus to 1, all right, that's a better way of saying this. I really shouldn't include ever that I have a boundary, all right, that is exactly equal to 0, because it's kind of not clear what the value of that function is going to be. It's roughly infinite at those points. Okay. All right. So let's look at this. I want to define what this function looks like. I want to say, what does the derivative of this function here look like? And I want to be able to sketch it out. So I've got f prime of t like that. All right. So how would I sketch that? What would that derivative look like from 0 here up to, let's call that 3 right there? what would I say that looks like? From 0 to 1, what's the derivative of f of t from 0 to 1? 1, right? So it's going to be 1. Now, what's going to happen here when I jump up like that? Yep, I'm going to see that Dirac delta. Then it's going to be a 1 again. Now, what's it going to do here where it goes down? It's going to be a negative delta. All right, now I'm going to talk about what it's about. I drew it twice the size here because basically it's a jump downward in this case from of 2, right? So what I do is I represent this guy. I say he doesn't have a meaning for his height, but basically this, what we say is the area of, let me do it this way, the area here, the area is equal to 2. All right, it's because if I think about the area that would be incorporated in that, if I took is going to be twice because of that jump of 2. All right, so we define it in terms of its area. So one of the things I want to, it's also important for me to talk about is this idea of what I would call a shifted impulse. Now we're going to talk about shifting and scaling and all that kind of stuff with functions here in a little bit more in the future. But let's say I have this guy here, f of t, which is an impulse located at t equal to 2. The question I have is, how do I express that? So how do I express, in this case, f of t in terms of delta of t? How would I do that here in this case? So it's a t, yeah, so it's a t equal to 2, right? So I've manipulated the t-axis value. So basically f of t looks like somehow it's going to be related to a delta of t, right? So how could let's do it this way. I've shifted it, right? So let's say I have delta of t. So you guys know if I have a shift, how does that get represented here? Well, it's some sort of a plus n like that, right? Some sort of a plus n. The question is, how would I figure out what that plus n value is? Is it plus 2? It's minus 2. How can I figure out that it's minus 2? So f of t in this case is this, t minus 2. How can I figure out that this makes sense? Well, what does delta of t look like if I were to draw it? Delta of t looks like this, right? Here's t equal to 0. Here's t equal to 2 shifted down from it, okay? So how can I figure out that this guy here is delta of t minus 2? Why is it minus 2? Well, so how can I do a check to see that this makes sense? Well, what happens if I say to myself, what is f of 2? What is f of 2 going to be? It's going to be delta of what? 0. Right? So what I can see is that when I plug into this function, the actual time value, t equal to 2, right? When I plug in t equal to 2, I get basically the same value of the function delta that I have for delta when it's equal to 0, right? When t equals 0 in the delta function. And if I plugged in f of 0, for instance, that's going to be delta of what? Yeah, so it would be of minus 2, right? And what is delta of minus 2? We said that has to be what? What is the delta function at minus 2? What's that? What was the delta function? What was the delta function at 2? What is the delta function at t equal to negative 2? So there's the delta function up top. What do we say was true about the delta function at all time values other than 0? 0, right? There you go. So delta of -2 is equal to 0. So if I look at this, basically, if I plugged in every possible value of time into this function, what I would see is that it should match up with what I know about the delta function. I look carefully at this argument here, the argument of the function, to make sure that it matches up with the function that I'm plugging into. Now that's going to get a little bit trickier when we start doing some of the manipulations that we'll start doing on Friday. But this is kind of an important thing to remember. And what this works out to be is if I shift a function to the left or to the right, so if I shift it to the right, I put a minus sign, which I can think of as a lag, because basically what you're saying is, yeah, at t equal to 0, what was at t equal to 0 is now at t equal to 2. So it's happening later in time. So there's a lag to that. If I move this guy to the left, that's where there would be a plus. Now you can just remember that, or you can see it's fairly easy to plug in the values here. You plug in the values of t equal to 0 and see that it equals whatever that underlying function is at that same time. All right, so you plug in those values to check it that way. The reason that becomes important is I'm going to start doing stuff like this. It's going to be like 3t plus 6. And then you have to say, well, what do I do in that case? All right. So that's the next problem for us to worry about. But that's it for now. So if I think about this, I've got this function. All right. How would I define this function here? So this f of t. This guy's the summation of a bunch of different impulses that are shifted from each other, right? So how would I express this? Let's do it this way. So it looks like I'll write my f of t over here. So let's deal with this guy. How do we define this guy right here? The first one. What is it? Just delta t on its own. Like that. How do I deal with this one here at t equal to 1? So I shifted it to the right. Yeah, so I plug in for this guy. Do I put a plus? I put a minus here and I say delta of t minus 1. And if I want to check, I plug in for that particular function, right? If I plug in t equal to 1, I get delta of 1 minus 1 is delta of 0. So this function here is like this guy at t equal to 0, right? That's the way to sort of think about that. So what about this one here at t equal to 2? How would I write that? Plus, yeah, delta t minus 2. And then if I get to this one, it should be fairly simple now. Minus delta of t minus 3. And then basically I keep following that pattern. Okay. So let's say this went on for forever, right? How could I begin to express that? You use the summation. All right. Now, I don't want to get into that just yet, because that's probably going to confuse a lot of people if I do that. But the summation notation is something we're going to touch on later. All right. What's that? Yeah, I mean, summation, it kind of deals with things that I could build in a for loop if I'm writing code, right? But I think about this, yeah, this is basically it's some sort of summation of all these things. So I would use that sigma function, which I think messes a lot of people up to think about. So I don't want to go down that road too far today. All right. All right. One of the things I've already kind of touched on, but basically, if I say I have alpha of t, right? So I have this scaling factor alpha. I call that a scaling function. I call it scaling because what I'm doing is I'm multiplying it. I'm scaling. I'm making it bigger by something, right? If I look at this, what that means is the area under this guy is alpha times bigger. Okay. Now I'm gonna if I have this here, this guy here would be 2 delta of t. All right, the important thing for me is this idea of what I'm calling a sifting property. Okay. So if I have delta of t minus t, it's an impulse function that has an impulse at t equal to capital T. All right. And f is some other function. Okay. So let's say I have this. I have, I don't know, f of t goes along like that. And then I have, let's say this function delta of t minus 3. So delta of t minus 3, where would that impulse be located? Actually, let me do it this way. Delta of t plus 3, where would that impulse be located? Minus 3. Yeah, so here at minus 3, this guy would go up. Now, if I said to you, compute for me f of t times delta of t plus 3. So f of t times delta of t plus 3. What do you think that would do? What does it seem like that should do if I multiply these two functions together? This function is 0 everywhere except at t equal to -3. What do you think it's going to do? What does it seem like it should do? Yeah, basically, well, basically it's going to, by multiplying them together, it's going to pull out the value right there at t equal to 3. So it's going to pull out f of -3, right? We call this the sifting property. And the way I define it is I got to do the integral, because this, what's true is delta of t dt is equal to 1, right? When I multiply it by a function, what it does is it says I pull out the value of the function at that point where the impulse is located. All right, so it's sifting, basically sifting out, it's pulling out a property. Now, where this is a useful concept, may not seem useful here for like, well, what's this for? So if I think about where this could apply is something like if I have an analog to digital converter that is sampling a signal, then I'm basically sifting out values from a signal at a particular point in time. So if I want to, again, back to my very first point in the class today, so we make mathematical models for physical processes in the real world. So if I'm sampling a signal, that's a physical process that I want to model, right? So a physical way to model that would be to say, take a signal, call it f of t, and multiply it by something like this guy, right? An impulse train. So some sort of multiplication of impulses. Why is that important? It's important for me to have that model because if I need to do something like this kinds of problems you have in the project, and I need to do some kind of thinking about how to design a system, then I need this kind of mathematical framework to be able to think through how to design that system. So this gives me just a mathematical way of thinking about certain common real world problems like that. All right, so let's say I had this. So I take the integral from -2 to 3 of this whole thing. All right, so before I get too far, let's draw what this looks like here. So I have f of t times this crazy looking function, okay? So I'm gonna call this function here g of t, all right? So let's draw what g of t looks like. All right, 2 plus delta of t plus 1. So let's start with 2. What's that look like? Just the number 2. All right, so this guy would apparently be a height of 2. Okay. Delta of t plus 1, where's that? Yep, at -1. And we'd show it having a height of 1 like that. Okay. Then what? -3 times delta of t plus 1. Where would that guy go? Where would he go in time? T equal to 1. And where would I draw him? So here's -1. Here's 1. You're pointing down, and how far down would it point? So it would point. So yeah, here's 2. He would point down to -1. Right? So this, like, would point down to -1. Okay. And then where would the next impulse be? Yeah, t equal to, yeah, so -3. So it would be like here, here's -3. And it says +2, so where would that go? Yeah, like that. All right. So yeah, I'm not sure how I want to, I guess the height of this guy is, the area under that guy is 2. Like that there. The area under that is 2. So this would be 2 plus 2 if I'm talking about the value there. And this guy would be -3. Yeah, the area under this particular impulse is -3, which is what got it to be sitting at -1. So that's the way we sort of express this, right? So that is now my function here. All right. If I were to look at this sifting property thing, I could look at this as just, I think of it this way, integral from -2 to 3 f of t. How can I break up if I have a summation like that for all these integrals? So 2 plus something. How do I express that integral? Couldn't I say that this is f of t times 2 dt plus the integral from -2 to 3 of what? F of t times what? Delta of t plus 1 dt. And then basically do that for all of the other ones, right? So, all right, so this first guy here, I mean, yeah, I need a function here, but it's the area under that function. If I say this guy from -2 to 3, what is the integral f of t from -2 to 3 of delta t plus 1? What would that be? What would that give me? What value of f? It pulls out a value of f. What value of f would it pull out? So what does it pull out? First of all, delta t plus 1. Delta t plus 1 sits where? At t equal to what? -1. So it pulls out the value at what? F of -1. All right. So whatever f is at that value is what gets sifted out. Okay. Then I can say, well, what is f of t times -3 delta of t minus 1 dt? And it's the integral from -2 to 3. So what would that be? What value would that pull off? -3 times f of 1. All right. Then I'd have one more to do, right? The value here at t equal to 3. Or sorry, I have the last one would be integral -2 to 3 f of t times 2 delta of t plus 3 dt. What would that pull out? What location would that pull off? -3, with one exception. Is that in the bounds of my integral? No. That would be 0. Right? Because it's not defined. The delta function is not defined in that particular range. Right? It would have been 2 times f of -3 if I had different boundaries. Okay. So this sifting property, these things are not particularly hard to think about. What they're good integrals to get because there's really no work. You just got to look at it to know what values that you pull off, and it's honestly causes a lot of people to get tests back and go once they see how easy the problem was that they got wrong. All right, so it's a useful concept, and we'll use more of it as we go in, particularly into the second project, we'll use this idea for modeling some stuff in the second project. All right, that's it.